doing some problems. So to summarize, we have 4 types of transitions. The first one was isobaric, where we would move from state 1 to state 2 at constant pressure. And the arrangement with that one was that we had work that, in this case, when we're moving to the left, we were applying to the gas. There was energy that was going to flow in or out of the system in the form of heat, that was Q. And there's also this possibility right here that the internal energy or the temperature of the gas could change. The way you could see that would be that we had isothermals here and here. So it looks like we went from one isothermal to another isothermal in doing that isobaric process. So probably there was a temperature change to watch out for as we did that. So that's one good common sense way to keep that in mind. If we do a transition now to state number 3, we did that with isovolumetric. The arrangement there would be, because no work can be done, the amount of internal energy of the gas gain or loss is equal to the heat that flows in or out of it. So very easy to keep track of. The third type of transition was one where we had an isothermal one that happened slowly enough that we could return back to our original state. And because it was slow, we always allowed the temperature to stay constant. The internal energy of the gas always stayed the same. So that U term disappears, and the work we get out of the gas this time is equal to the energy that we put into it, or vice versa. And the way you could see the whole thing fitting together to say that, again, this is a system that goes clockwise. It's one that's going to give us work from the system would be like this. In the first stage, the isobaric transition, we did work on the gas, and so the area under that part of the graph was just like that. In the third part of the graph, we had a different arrangement that looked like this. We moved from state number 3 to state number 1, and the area under that graph was like so. And so as you can see, going to the left in the first stage was negative work. Going back to the right, going from state 3 back to state 1 was positive work. And so what we're left with at the end of the day is this area right here in the middle that's actually the net work done by the system. And so since the work was done going from 3 to 1 on a higher isotherm than the work going from down here from 1 to 2, then we ended up with positive work in this system. Now, there's not much to be said about the adiabatic transition that we haven't already said, but there's one important point that we can also make. If we had a transition between 1 and 2, and we said an adiabatic might have a slide between two isothermals like that, the amount of work that would be done would be real. It would be here, and we would shade in this area right here underneath the pressure volume graph. That's work, if we look at it, that was coming out in this direction. So because we were sliding to a bigger volume, that was work that was going to come out to us and be positive. The thing is, if I flip that equation around, when work is positive to us, it's negative to the gas. That whole idea of what's doing work and where's the negative sign is a big issue. So usually what we think of as is that work that comes out is positive. That's work done for us. Work that would go in on the gas would be negative to us. And that's how we keep track of it. This example, which appears on page 413 in your textbook, is a good example of ones where we need to really read the question. What they're asking is a little simpler than what you might think they'd be asking. The question is, if we have a gas that goes an isothermal transition from A to B, like so, and then goes from B down to D in an isobaric change, and then does an isovolume change from D to A, how much is the work done? But what they say is the amount of work done from B to D to A. So hold on to that thought for 1 second. I'll show you how we would have done it. Here's a complicated example in the chapter. What they'll say is something like this. In sliding from B to D, you know that there's going to be a negative change in volume. And so the amount of work, let's call it red, for let's say it's negative work, it's work that we put in. Then a transition happens over here where we slide the gas up back to state A. And as the gas slides down isothermally, we get all of this work, except all of this work now is positive work. So that's work done by the gas for us. And so what's the difference between the two is this amount of energy right there. and that would be the overall amount of work that was done by the system for us. So that would be positive work from our standpoint. Now, that's not what they're asking, though. Watch what they're asking is actually simpler. In this question, since they say, just tell us about the work that's done between B, D, and A, what we can say is that we know we lost 8 liters worth of volume, so delta V is negative 8 liters, or negative 8 times 10 to the minus 3 cubic meters, to keep it metric. And that happened at 1 atmosphere pressure, around 101.3 kilopascals. And so the amount of work done from B, D to A is just this amount of area right here. And that's all you have to know. And that turns out to be about minus 1,600 joules worth of work. There you go. So that's that part. The second thing that they ask us is to figure out the overall amount of heat energy that went in or out of the system. And to do that, think about this transition. When we went from point D to point A, the only way the gas would do that, to keep a steady volume while cranking up the pressure, is that we dumped energy into it. So we did add some Q during that step. We had to. But now here's the key idea. Realize that we end up back at point A, so we're at the same pressure, volume, and we're at the same temperature that we were initially. So since we end up at exactly the same temperature, that means overall the change in internal energy of the gas, because the temperature was constant, is equal to 0. So we knew from part A that the work that we did was, to us, negative 1,600 joules, and that the gas had to have had energy added into it at this step, and the overall amount of energy that we had to add to it there would have been in the form of heat, would have been in the form of Q, and so the answer to B has got to be, since this whole thing adds up to no overall energy change, is that we added 1,600 joules worth of heat. So pretty easy. The last question we're going to take a look at for now is on page 434 of your textbook, and it's question number 10 in the homework. In this one, we have a gas that transitions from state A on down to state B, and then over to state C. And if you've been paying attention, then you should have a lot of strength about you in terms of how to solve these problems. So in state A, we've got 2.2 atmospheres of gas and holding a volume of 6.8 liters. And somehow we managed to hold that volume constant while relaxing the pressure. So the only way that that could happen would be that heat flowed out of the gas. So we know that there's a Q equals negative step right there. The gas then slides over from B to C, so there's a positive change in volume. And that actually gets us right into answering the first question, so I might as well jump on it right now. The area under that graph is going to give us P, pressure, times change in volume, and that's easy to figure out. When you go ahead and get the change in volume, it's 9.3 minus 6.8 liters, 1.4 atmospheres. Whole thing adds up to 355 joules. So the answer to question A right up there is 355 joules. Now, question B, what's the overall change of internal energy of the gas from A to B to C? I hope you've been noticing that's an isothermal right there. And if you know that the internal energy of the gas is directly proportional to the temperature, if we're at the same temperature in here as we were when we started, then the internal energy change of the gas is equal to 0. And what that does is turn out to give us the answer to a very handy question. We knew that heat here had to be negative, and if we're at the same internal energy of the gas, then all we need to do is bring up the central formula to the whole section, which is the conservation of energy. The change in internal energy of the gas is the heat that we dump into it minus the work that it does. And if you look at these two things, then you'll figure out that the heat energy that we supplied right there was 355 joules. And that's as easy as it is. So again, the problems in Giancoli aren't too hard. You should be able to handle them, but draw a PV graph when you're in doubt. And see you soon. Bye-bye.